guess we can start. So, welcome everyone to our talk, Making Complexity Simple, using a universal language to make tech principle accessible. Before we start, let us introduce ourselves very briefly. I am Michele, I'm co-founder and CTO at Orama Search, and I'm here with
Angela. Hello everyone, I'm co-founder and head of design at Orama Search.
So we co-founded Orama Search with another couple of great professionals in the industry, and we co-founded it in order to create a new kind of full-text search engine that runs wherever JavaScript runs. So we truly believe in JavaScript and we truly love it. I know that might sound strange. But basically, if you're interested in learning more about how we are willing to change the market for full-text search engine, we will be there after the talk, of course. And while founding a company on a domain that is strictly technical, we found out that there are some problems in explaining what we are doing, especially to colleagues that are not super technical, to stakeholders from other companies, clients, and people that are not developers. So, first thing we noticed, a big problem for us was that developers constantly face resources that are difficult to understand and require high cognitive loads. And that's specifically true whenever you go into explaining how algorithms for full-text search works, why you should adopt either a solution or another. The challenge in that sense is that the topics are complex and abstract most of the time. So how can we make this a bit more accessible, right? So how can we make complex things simple? This is where Angela kicks in.
Yeah, thank you, Michele. So once we identify the problem, so document can be really complex, we need to find a solution. And to do that, we follow this three-step process, but let's see in detail. So first thing, we define. This is a convergent phase. It means that its focus is to find a well-defined solution. And this is a co-design phase. It means that the designer and the developer works together to find the solution. So first thing, we have to understand the pain point that our users are having, and of course, understand our users, so define the personas. The personas are fictional characters based on the research in order to represent the different users that we have. So once we have all the pain point and we know our user, we can decide what will be our solution. So, and based on the problem before, we decide to create content that are quick, fun, and easy to understand. The second phase is the develop phase, and also this one is a co-design phase. And it's the phase where we decide how to represent the solution identified in the previous step. So what will be the shape of this content? What, do we have to use metaphor to represent them, or maybe can we use a real-world example? In this case, we are talking about video, so this is the moment where we are creating the storyboard, decide how to show the information. And to do that, I'm a digital product designer, and in this phase, we normally follow the 10 heuristic of usability of Nielsen. For this kind of product, I listed only 3 that are the one that I use. So the match between the system and the real world. It means that the solution must speak the same languages of the user. We need to use familiar words and avoid internal jargon. And also, we need to follow real world convention and a logical order to show the information. The second heuristic is consistency and standard, and it based of Jacob's law, it's a usability law, and states that people spend more time on using other digital products than yours. So their user experience is set, the expectation, is set while using that product. So we need to use standard and convention to minimize the cognitive effort. The last heuristic is recognition, read, and recall, and this is important because humans have limited short-term memory, and we need to minimize their memory by making the elements easy to understand, and we also need to repeat this element during the solution. The last phase is the phase where we create what you are going to say, what the user is going to see. And it is an important phase because we build and strengthen the brand perception. It's also where we need to be accessible. It means that we need to use a language that can be understood by all our users. We need to provoke emotion and delight because appealing product result easier to understand and use the other products that are maybe less appealing. And aesthetic and minimalist design. This is the famous less is more. It means that we need to use only the elements that are requested and avoid all the superfluous.
All right, so starting from there, I'd like to ask you how many times, as developers or as non-technical people, have you been in a documentation website where you couldn't understand anything? At least once? Awesome, so I guess that's a common problem for everyone here. That's the problem we wanted to solve at the beginning. So we identified 4 principal ways of dealing with algorithms and data structures, for example, or problems of any kind in our domain that are very common to basically every digital product that involves software development in it. So we noticed that some problems can be simple but concrete, so simple to understand, and they also have a real-life counterpart where we can identify a real-world example in order to explain the concept better. Some other problems are concrete but pretty complex, so a real-world example might not be enough, it's not well treated. Other problems are complex and abstract, so there's no real-world example to explain them. And also, they can be abstract but simple, so we have a spectrum of complexity and abstraction that we have to deal with. For that reason, we wanted to make our documentation, we wanted to make our product easy to understand for everyone, and this is where we want to start by giving an example of how to make products and technical stuff accessible to everyone. We identified 3 algorithms and 1 data structure that we are gonna talk about in just 1 second. And we'll proceed like that. I will be explaining them as I was a developer, which I am, and 2 developers. And we will have a person that is not a technical person. She's a designer, and we'll explain this to everyone else. So I will be talking to Anish. She will be talking about to everyone. So how many of you knows Quicksort, for example? Fantastic. How many of you knows the Dijkstra shortest path algorithm? Fantastic. Levenshtein edit distance? Okay, I see the hands are going a bit down. Hash map data structure. Come on, yeah, okay. I was expecting that. Awesome. So, yeah, let's start with Quicksort, which is simple because it's a pretty simple algorithm. And it's also pretty concrete, so there is a real-world counterpart for explaining how it works. I will explain this as a developer, then Angela will kick in. She made some amazing videos to explain them better than I do. So, what is Quicksort? Quicksort is a divide and conquer sorting algorithm that operates by selecting a pivot element from an array, then partitioning the array into subarrays, elements less than the pivot and elements that are greater than the pivot. It recursively applies the process to the subarrays, ultimately resulting in sorted array. So this is typically the kind of explanation you have in every single documentation website with that image. Not so good, right? I can also show you some code, and of course I will show this in Haskell. Why not? Some easy code to explain, right? Fun enough, this is pretty easy if you know Haskell, I guess. It's not a good Quicksort, but it gets straight to the point. So you basically have like ordinable type class that says, okay, every single element that can be ordered, so integers, chars, floats, or every single element that extends the order type class, it's an input for the function, and we return the exact same type as an output, and we'll recursively apply that function to the pivot. And that's really it. But the first time I told this to Angela, she was like, oh my God, yeah, no, please. Yeah. So,
well, also now, all this hand up, that's okay.
So I guess you have a better way to explain this,
Let's
right?
try. So we start with Quicksort. Quicksort was developed in 1959 by Tony Hoare, a British computer scientist who also won the Turing Award thanks to Quicksort. Its goal is a sorting algorithm, so it's to order a list of items in the most efficient way possible. And let's see how. We are going to use the example of a deck of cards. So let's say that we have a messy deck of cards, and we want to sort them in an efficient way. But we don't want to do that. We don't have time. We are lazy. So we are going to ask Quicksort to do that for us. What is going to do? Is going to take a random card from the deck, call it pivot card. Then it will go through all the cards on the deck and mark the smaller number and the bigger number. Then it will move the smaller number to the left and the bigger number to the right of the pivot point. But our deck is not ordered yet, so we have to repeat the action. This time, not on all the deck, but just on the left side of the last selected point. So again, we select a random card, we mark the smaller number and the bigger number, and we move them to the left and to the right. We are almost there. Our deck is almost well listed, so we need to repeat the action again. We select another pivot point and move the smaller and the bigger number. And now our deck of cards is well sorted. And Tony O'Hara is also happy.
Yeah, I guess he is. He won a Turing Award because of that. So that's really cool. And at the end of the day, my question for you is, which kind of explanation would you find more appealing? Which kind of explanation would you remember at the end of the day, right? So this is where I believe software development by itself, it's not enough. This is where, for example, as Orama Search, we wanted to invest from the very beginning into design and into user research to understand how we can actually make things a bit more easier to understand and accessible. So we saw something that was, simple and concrete. Let's go somewhere a bit more complex, but yet still concrete. So the Dijkstra shortest path algorithm. So yeah, what is it? So basically, the Dijkstra algorithm, it's a graph traversal technique that finds the shorter path between a starting node and all the nodes in a weighted graph with no negative weights. It iteratively selects the node with the smallest tentative distance from the starting node, updates its neighbor distances, and marks the selected node as visited until all the nodes has been visited. Pretty clear, right? Easy.
Easy.
I will show you some Python. I know you wanted Haskell. I know. It was too difficult to code in Haskell. So here's a Python implementation. It's a pretty dense algorithm. Like it's not that complex once you understand how it works. And this is a typical example. You pass a graph to a function, a starting node, and we return a dictionary containing all the distances between the starting node and all the other nodes in the graph. And this is pretty simple, right? It is. But if you're not a technical person, this is likely to be your reaction, right?
Exactly.
So please explain this better to us.
Let's try again. So Dijkstra algorithm was created by Edgar Dijkstra in 1956 in only 20 minutes, because, fun fact, he said that he created it while drinking a coffee in a bar with his girlfriend, so very casual. And his goal is to find the shortest path between 2 points. Let's see how. So let's use this example. I think that it's a common example. And let's say that we are craving for an ice cream, but of course the ice cream shop is on the other side of the city. And we need to understand what is the shortest path to go there. So it could be through the donut shop or maybe through the bank and then the coffee shop. Let's find out better. Let's ask Dijkstra the best way. And Dijkstra will update the estimate, so the required time to travel from one node to another. The nodes are our point of interest, like the donut shop. And he will also choose the next vertex, where the vertex are the road. So he will repeat these 2 actions for us. So now we are on the starting point, and we don't know the time to arrive to our node, so the point of interest, but we do know the time that is required to travel each road, each vertex. So the first thing that Dijkstra will do is, from the starting point, go to the next point of interest. So we will go to the donut shop, update the time, and we will also go to the bank and update the estimate, so 3 and 2. Now, what it's going to do, starting from the point with the lowest time, so the bank will repeat the action. So we'll go to the nearest point of interest. I will update the time to 7 because 2 plus 5 is 7, to the park, and the time to 5, and also to the donut shop. But this time, it won't update the estimate because it's bigger than the one that is already there, because 2 plus 2 is 4. Now, we need to repeat the action. So for the donut shop, we'll go finally to the ice cream shop, but we're not sure that is the quickest way. So I will repeat the action again, starting from the donut shop. Here we go to the park, update the estimate to 4, so it's lower, and finally it will arrive to the ice cream shop and have the time to 7. So this is the fastest way to arrive there. We can finally have our ice cream and maybe also find Jaxa drinking our coffee.
Fantastic. So we just saw a couple of examples in the concrete realm of things. So Quicksort and Juxtra, basically two kind of algorithms that has a real-world counterpart. Now I guess it's time to go into the abstract one, and we will go there with a data structure, the hash map, which is very simple, but yet pretty abstract. As developers, I'm quite sure that every one of us knows hash map. I want to give you I got to be honest, this is a pretty naive explanation of what a hash map is. It's not super accurate, to be honest. I'm not going to go through this, but this is, if you ask a developer, they're going to send you something like that. But OK, let's explain it a little bit better. I would be ashamed if I didn't do that. So let's say we have key value pairs, right? We have, I don't know, SFO, which stands for San Francisco. So SFO is the shortest version, and San Francisco is the value. We create an array of 7 elements, and we put our key through an hashing function that will return a number between 0 and 7, because these are the maximum length of our array. And in that case, will give us 4. So we will put in the 5th position for our array, so the 4th index. And that's basically how a hash map works, that this is likely to be very efficient during retrieval and insertion. But again, it's not super clear to someone that it's not technical, right? So we got another video for that.
That's right. So, hash map. Have you ever had that feeling when you are searching for something, but you really can't find it? Hash map is here to help us. In fact, his goal is to store item with an identifier in order to make the insertion and the retrieval process very efficient. Let's see how. But let's use a wine example. So let's say that we are a wine collector, because it's OK to lose a socks, but no, not OK to lose a wine bottle. And and we keep our wine in a cellar. But of course, we have a lot of bottle of wine, so we need help. And Hash work there and help us. So what he's going to do for us, Hash? Each time that we give him a new bottle, he will convert his name into a number. And that number represents the position where the wine is stored in the cellar. So what this means that the next time that the big day comes and we want to party and drink our wine, we can simply ask to Ash to bring the Rioja, I hope I'm saying right, Alta, and he will remember the position and bring it to us.
I guess it was the great place to misspell, right?
Yeah, Spanish name.
We will ask for clarification later. All right. Yeah, we're almost there. We just missed one, which is the Levenshtein edit distance algorithm, which is complex and abstract. So yeah, we couldn't wait for this moment to come. And again, what is the Levenshtein edit distance? It's this thing.
Of course.
Super clear, right? So it basically says that given two strings, A and B, the minimum edit distance is defined as the sum of the minimum of 3 operations: deletion, insertion, and replacement. OK, let me give you a little better of an example. So let's say we want to convert Honda into Hyundai. we have to perform 3 operations. We have to insert a Y to replace a O with an U, or insert an I at the end of the word. Or we can do in slightly different ways, but at the end of the day, we will just have 3 edit distances. So basically, we will require 3 edits to perform this operation. And that becomes even more clear, right, if we start to show that into a dynamic programming table, where it basically keeps track of every single modification for the word, in order to arrive in that sweet spot, or maybe you can see it, but it's in the bottom right corner, where 3 is the edit distance between 2 words. And it's using spell checkers, search engines, to provide basically spells check. So if I search for something and I cannot find it in the database, I can see words that are very similar, so with a minimum edit distance, and say, oh, maybe you're searching for something else. But again, not super simple. I guess Angela can explain this better.
Let's try. Levstein algorithm is also known as clumsy typewriter's best friend. So if you are like me, that each time that you write something, you are making mistake, you're going to love this algorithm. What is its goal? Its goal is to tell us how much two words differ and how many steps we need to transform one word into another. And to do that, it performs 3 operations: the insertion, replacement, and the removal of the individual letter in a word. So let's say that we want to transform the word moon into lion. What the algorithm is going to do for us? Levstein will take the first letter, the M, and transform it into an L, the O into I. It will keep the second O. It will also keep the letter N, as since we want 2 lions, it will also add an S. So the Levstein distance here is 3. But does it mean that next time that you are writing in your favorite e-commerce and you make mistake and the website suggests you a different word, you have to thank Levstein algorithm?
Absolutely. So this is basically 4 examples of how you can make things a bit more accessible to everyone. And we have a couple of takeaways that we'd love you to take home from this talk. So first of all, you have to know your target. And when I say that because when you're talking with a stakeholder that it's not typically technical, if I think of, I don't know, a client, a project manager that it's not super technical, we want them to be able to understand what we are talking about. Because if I go to a project manager, for example, and say, okay, you know what, I will take 3 more days for implementing this, they won't understand what you're talking about unless you explain with simple words, right? And finding relationships between concepts and real life, it's the only possible way, at least for me, to understand what's going on. So for that reason, I truly believe, and we truly believe, that in order to make things accessible, we have to explain them like we are 5. And if I cannot understand them like I'm 5, please explain me like I'm 3. Because there's nothing wrong in asking for help when you have to understand such complex topics. And one very last thing before we leave, accessibility matters. And I'm not talking just about web accessibility, which is another super important topic. It's not something that we want to leave on a side, but accessibility also means being able to explain to people what is the core of our job, what is the value that is intrinsic in what we are doing. This is what it's really important for us to do, especially if you're building a product that is extremely technical. And yeah, I guess that was all for us, and we will be there for questions, and thank you all for being here.
Thank you.
I will keep this slide while if there's anyone with questions, I'll be glad to answer. If there are no questions, we will go drink some water. All right. Thank you all.
Thank you.